Welcome back everyone. In the previous lesson we looked at rate laws and the method of initial rates. In today's chemistry lesson we are going deeper into chemical kinetics by studying integrated rate laws, half-life calculations and the Arrhenius equation. By the end of this lesson you will be able to calculate concentration at any time, identify reaction order and handle temperature based exam questions. Now having talked of that, now the first question which comes in our mind is why integrated rate laws? So far we have been answering the question how far is the reaction. Now when we come to integrated rate laws, we answer a different question, which is how much reactant remains after a certain time. So one thing you should know is that each reaction order has its own equation, so identifying the order is very important. As I said in the previous video that there is zero order reaction, first order reaction, second order reaction, even third. So each order reaction has its own equation, and that's what we are even going to look at today. So it's very important to know the formula of each order of reaction. So let's start with the zero order reaction. So for a zero order reaction, just as I said in the previous video, a zero order reaction, the rate is independent of concentration. And we said the rate is equal to K. So for a zero order reaction, this often happens when a catalyst or surface is fully saturated. So the integrated rate law for a zero order reaction is A, which is final concentration, is equal to initial concentration minus Kt, where K is the constant. So as you can see this formula, it answers that statement I said, why integrated rate law? We said integrated rate law, it's all about how much reactant remains after a certain time. As you can see in this formula, we have the final concentration here, the initial concentration minus constant times the time. So you can see that there was the concentration at the beginning and a certain time has passed with a constant. Now what's the concentration that's going to remain? So that's integrated rate law. It's all about what reactants remain after the reaction. So this is the rate law for what? For zero order reaction, the integrated rate law. So let's look at an example. If we have been given, for example, the initial concentration of 0.8 mole per cubic decimeter, so we have been given initial concentration to be 0.8 mole dm power negative 3. So like given that the initial concentration is 0.8 mole, then the rate constant is 0.02, then the time is 20 seconds. So for us to find the value of the final concentration, we just need to plug it in that formula. This one, we'll be able to find the final concentration. So let's go ahead and solve it. So final concentration, I'm sure, let's hope you have written it somewhere, the question. Final concentration will be just equal to 0.80 minus 2 or 0.02 by 20. You should also be writing the units. The answer you are going to find is 0.4. The units is mole per. So that's our final answer for concentration. So that's how the questions are going to be coming. They are just going to confuse you. Maybe they are just going to give you a statement. For example, a reaction maybe start the initial concentration is this and this, and it undergoes a reaction after some time. What can you find the concentration? So you just need to find where the initial concentration, where the rate constant, time. Again, they can maybe require you to find the initial concentration instead of the final concentration or the time. That's just the formula you use. The key is to just know the formula for, is it zero order reaction, first order? So for zero order reaction, that's the equation we are going to be using and nothing else but that equation. So know it and also differentiate it from the other orders. So let's talk about half-life of zero order reaction. So I'm going to be doing the integrated rate law, then I go for half-life of the same order of reaction. So half-life of zero order reaction. So you should know the formula for zero order reaction in terms of half-life and first order and second. So it's just initial concentration over 2K. So this is the equation you are going to be using. And notice that half-life depends on initial concentration. So when you are calculating the half-life, if it's in terms of zero order reaction, this is the equation you are going to be using. Initial concentration over 2K. So just know that formula and everything will be easier for you. So chemical kinetics is not difficult, guys. You just need to practice and know the formulas. Let's talk about first order reaction. So for first order reaction, they are extremely common in chemistry and biology. The rate for this one, the rate is proportional to concentration. Integrated rate law for first order reaction, it's similar to zero in that for first order we are going to be putting in, if you can remember, on zero order reaction there was just the final concentration here, but here it's in lean final concentration. Again, lean. So this you can pronounce it, I don't know if it's lean or in according to how you were taught, but this is the formula. So as you can see, it's just similar to zero order in that this one you just introduce the what, the lean. Or this formula can also be written in this way. So when you are calculating, it depends on which one will give you an advantage at that particular time. So they are one and the same thing. Lean, initial concentration over final concentration is equal to KT. So this is the formula for first order reaction. The thing that you should just consider in zero order in first order reaction, even in zero order reaction, the unit for the rate for the constant is very, very important. They usually even ask it in exams. So for zero order reaction, for first order reaction, the unit is always S inverse. What about zero order reaction? For zero order reaction, this is the unit, mole per cubic decimeter per second. So it's mole dm power negative 3 S inverse. So know the units for the rate constant, which is K. For first order, it's simple, it's just S inverse. So this is one of the things you should know. They usually ask it in multiple choice. What's the unit for rate constant in terms of zero order, first order, or second order? So there we go. Now let's talk about half-life of first order. So let's go again. Half-life of first order reaction. This is one of the simplest equation in terms of half-life. So half-life of first order reaction is equal to 0.693 over K over K. So this is the big example. If half-life is constant, then the reaction is first order. So when we are given, can you calculate the half-life of a reaction, maybe of its first order? Just say 0.693 over what? Over the rate constant. So this 0.693 doesn't change, it's just a constant. So that's all about it, first order reaction. So just know the formulas and everything will be simple when you're talking about integrated rate laws. When we are talking about second order reactions, these they depend on the square of concentration or two reactants. And the integrated rate law for second order reaction is 1 over final concentration is equal to KT plus 1 over initial concentration. So this is the formula we use when you're talking about second order reaction. So as you can see, this one K is negative, so is positive. For the previous ones, the first order and the zero order, the negative there was negative KT, but here instead of negative KT, it's what? It's positive. What about half-life of a second order reaction? Half-life is just, so I'm really emphasizing, know the formula, these formulas. 1 over K A initial. You should see the difference. For first order it was K is 0.693 over K. For zero order reaction it was A initial over, which is initial concentration, over 2K. Again, even for second order reaction, half-life depends on what? On initial concentration. The only difference is here it's 1 over K initial concentration. So that's all about integrated rate laws and the half-lives. It's not that difficult. You just need to know the formulas. Yeah. So the next thing that we are going to look at is Arrhenius equation. So temperature has a strong effect on reaction rate. That's why we usually we have this formula. We call it Arrhenius equation. This formula goes like K is equal to A E power negative K A over R T. Oh, I made a mistake here. Not negative K A, it's negative E A, which is the activation energy. So this is the formula of Arrhenius equation. A E power negative activation energy over RT, where R is what? Is a constant. For exams, we mostly use the two-temperature form, the Arrhenius two-temperature form equation, and this goes like this. So this is the formula we use for two-temperature form. So this is lean K2 over K1. This is temperature, but in kelvins, is equal to activation energy over R, then square the brackets 1 over T1 minus T2. Oh, the K2 and K1, they are constants, the rate constants. While 1 over T1 is temperature in what? In Kelvin. So this is the formula we're going to be using. So they are going to, can you find the activation energy? They give you, for example, the two rate constants and their temperatures in kelvins, or you change them in kelvins. Then you just use the formula, this formula, ln K2 over K1 is equal to activation energy over R, brackets 1 over temperature 1 minus 1 over temperature 2. So that's all about integrated rate laws, half-lives, and also Arrhenius equation. So the exam tips I'm going to give you is, before calculations, always ask what is the reaction rate, which formula applies. So markers love correct formulas, units, and clear steps. So that's for today's chemistry 112 lesson on chemical kinetics. If this video helped you, please like and subscribe for more videos, and share with a classmate or a friend. Next lesson, we are going to talk about reaction mechanisms and catalysts, and that will be the end of this topic, chemical kinetics.